Hi everyone, this is Mr. Scott and I'm giving you an inelastic collision screencast today, trying to get you guys used to doing the calculations with this specific type of collision. Up to this point we've introduced a couple different situations in which collisions can happen. We've had explosions/separations like the moving inertia lab, and we've also taught you about elastic collisions, which have things bouncing and not deforming when they make contact with surfaces. Easiest examples would be like a tennis ball, even though it's not a perfect elastic collision, hitting a ground, or some type of other rubber bouncy ball. These things usually don't deform very much and they come back to the same height at which you dropped them, and they stay in their same original shape. Inelastic collisions are the exact opposite. They usually can deform, become tangled with each other, something catches something else, and they stick together afterwards and could come to a stop or continue to keep moving depending on the situation. However, in both types of collisions, momentum is always conserved. It's always conserved, still conserved. Tell Judge Judy, it's the law. So just like how you've learned in previous classes like biology and chemistry that energy and mass must be conserved, momentum is also conserved. So the moving inertia that something has before a collision is always going to be equal to the moving inertia that the same something or an entire system will have after. So let's give you an example of a quick demo that we can do in class where we shoot one hover puck towards another hover puck that's still, and then they connect and move on as a system. So here, we tell you that the velocity of the first hover puck is 1 meter per second, it collides into a second one, and each hover puck has 0.3 kilograms of mass. Then we ask you about the speed after the collision. So the way you start any momentum problem like this is to always say that the momentum before equals the momentum after. And here, beforehand, we only have one momentum. Because one hover puck was stationary and had no velocity, that second hover puck is going to have zero momentum, and the only total momentum of the system is what the first hover puck had coming in. So after the collision, they become a combined mass, and they move at some velocity. We're going to call that P with a subscript of 1, 2. We'll change that subscript up, but it still represents the same thing. It's the momentum of the combined hover pucks after the collision has happened. Now, since the mass is now double of what it was beforehand, you can expect that the velocity that they'd be moving at would slow down after the forces are applied to both hover pucks. And since it's exactly twice the mass, you should have half the velocity afterwards. So in order to actually show your work and get full points on a quiz or test on a problem like this, the first thing you might have to do is identify, is this an elastic, inelastic, or separation event that's happening? Since two things are becoming tangled, it must be an inelastic collision, and now we set up our m's and our v's, given that the momentum before is equal to the momentum after. So beforehand, it's just the mass of the first hover puck times the velocity of the first hover puck. Afterwards, it's the combined mass, and since they're the same, we can just call them both m, times the velocity of the combination, 1, 2. And we set P before equal to P after and solve for what we initially were asked for, which is how fast do they travel together, in other words, V with the subscript 1, 2. The masses cancel out, we divide the 2 to the other side, and as we expected, we end up with 1 over 2, or V1 over a half, being the velocity of the combination after the collision. Since the hover puck initially was moving at 1 meter per second, and then the combination would be half of that, it's just 0.5 meters per second is your answer as the final velocity. So typically the hardest part of this chapter is identifying which type of collision is actually happening, right? If you do that incorrectly, you're going to be completely lost trying to solve for any of the variables like mass or velocity after you set up your equation. So, identifying that it's an inelastic collision with the two objects sticking together, they could be moving towards each other in the same direction. One could be still, like we saw in the previous example, but as long as they're tangling and becoming the same combined mass afterwards, we set up the equation with this. So m1v1 plus m2v2 equals m1 plus m2 times the final velocity of the combo. That is your equation setup. Now, because velocity can go either direction, it could be positive or negative depending on if things are moving towards or away, so you have to note that and decide which way you want to call positive and which way you want to call negative. while you're plugging in your values on any word problem. Okay, let's try another practice example. So in this one, we have radioactive man at 200 kilograms flying towards a cannon at 25 meters per second, catching a 10 kilogram cannonball traveling 400 meters per second back at it. What's the resulting speed and direction? So note, radioactive man is going to the left, cannonball is going to the right. They're going to collide, they're going to be caught. So that is like key wording telling you this is an inelastic collision. And just to keep things simple, we're going to define to the right positive and to the left negative. So knowing that momentum is always conserved, we can say momentum before equals momentum after. And beforehand, now, because both objects are moving, we have two different momentums with an opposite sign involved. So the momentum before will be momentum of the cannonball plus a momentum of radioactive man. We're going to use some color coding here to show you which is which, but that's M1V1 plus M2V2. When you substitute in the values for the mass of the cannonball and the mass of radioactive man and the velocities of both, you end up with P1 being equal to 4,000 kilogram meters per second and P2 being equal to negative 5,000 kilogram meters per second. Notice we made the 25 meters per second negative because it's going to the left. The total momentum then beforehand must be 4,000 minus or plus a negative 5,000 kilogram meters per second or a negative 1,000 kilogram meters per second. This also means that we should have the momentum afterwards being equal to a negative 1,000 kilogram meters per second as well. Afterwards, they combine and become a combined mass of 200 kilograms plus 10 kilograms, or 210 kilograms, and it's our job to figure out what the speed, or the velocity when you add direction, is of the combination. So here we set it up as M1 plus M2 times that velocity of the combo, or 1 comma 2, and plug in what we know. So that's going to be 210 kilograms times that velocity, and then being equal, because of conservation momentum, the momentum before being equal to momentum after, negative 1,000 kilogram meters per second, or what we found out on the other side of the equation. When you do some quick math, you find out that the combination is going to be moving at 4.76 meters per second to the left, and we know that because the answer came out negative. So radioactive man had a little bit more momentum initially than the cannonball did, and therefore the combination will stay in the same direction he was going to begin with. So hopefully you learned a little bit from that review of the inelastic collisions, and now let's see if you can apply it with practice file 4-1.